Okay, I'd like to finish up section 11.10 in this video here. We got a couple more examples left to do. In this first example, we're going to find the sum. I got a part A and a part B here. And now the idea with some of these problems in the book is to recognize it as a particular function. Okay, so like in part A, I got the summation as n equals 0 to infinity of negative 1 to the n times pi to the 2n divided by 6 to the 2n times 2n factorial. So let's see, pi to the 2n over 6 to the 2n, that's the same as pi over 6 to the 2n, right? And let's see, now this Maclaurin series represents cosine x, right? So cosine x, that is, let's see, the summation as n equals 0 to infinity of negative 1 to the n times x to the 2n divided by 2n factorial. Okay, so it looks like x in this problem is pi over 6, right? I have the same form as what I just showed you there. So x is pi over 6. And so all I have to do is find cosine pi over 6. And cosine pi over 6 is root 3 over 2. So when I add up all infinitely many of these terms, the grand total is root 3 over 2. Okay? Let's try part B here. So in part B, I have the summation as n equals 1 to infinity of negative 1 to the n plus 1 times 3 to the n divided by n times 5 to the n. Okay, here's 3 to the n over 5 to the n, that's 3/5 to the n. And then negative 1 to the n plus 1, that's the same as negative 1 to the n times negative 1. Okay, so I got a negative 1 to the n times 3/5 to the n. Let me combine those. So I have a negative 3/5 to the n. I still got this negative 1 in front of that. Okay, so now I'm looking at the summation as n equals 1 to infinity of the quantity negative 3/5 to the n divided by n. Okay, so what is the grand total from that? Well, let's see. So the thing here would be to recognize that I've got this function. So the ln of 1 minus x is the summation as n equals 1 to infinity of negative x to the n divided by n. Right? So, and that's what I have here. I'm just going to go to that Maclaurin series there. And so I'm going to have the ln of 1 minus negative 3 over 5. Okay, 1 minus negative 3/5 is 8/5. So the ln of 8/5, that would be the grand total from adding up all infinitely many of these terms. Okay, so there's a couple of problems like this in the book. Okay. Now, one reason why Taylor series are so important is that they enable us to integrate functions that we couldn't previously handle. Okay, so let's see, here's an example. So what if I wanted to integrate the function e to the negative x squared dx? That is impossible to integrate using the previous techniques, meaning the techniques that I mentioned in chapter 7 there. Okay, there's no way to know the exact antiderivative of this guy. It's an impossible problem. Okay, now if I had bounds, like I could find a good approximation of what the area under the curve would be, I could use Simpson's rule or the trapezoidal rule, or one of the approximation methods mentioned in section 7.7 there. I could use that. Okay, or let me just use a power series here. Okay, so e to the x, that is the summation as n equals 0 to infinity of x to the n divided by n factorial. Now I don't have e to the x, right? I got e to the negative x squared. So where I see the x, I'm going to replace that with negative x squared. And I'll be integrating the summation as n equals 0 to infinity of negative x squared to the n divided by n factorial times dx. Okay, that would be equal to the summation, or to the integral of the summation as n equals 0 to infinity of negative 1 to the n times x to the 2n divided by n factorial dx. Okay, and now I'm ready to integrate this. So I got an indefinite integral, so I need to make sure I remember my plus c's. So I got c plus the summation as n equals 0 to infinity. Now all I'm doing is I'm adding 1 to the power and dividing by the new power. Okay, so I'm going to have inside there, it's going to be negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 times n factorial. Circle that. That's the end. Okay. So now that would be important to know, because I can avoid using like a Simpson's rule or something like that, or or I can I can still do this problem. Like I don't know the exact answer. Okay, because this is an infinite series here, but there's still a way to get the answer. Okay, which is one benefit of Taylor's series. Now the interval of convergence is all real numbers here. So what if I let what if I wanted to integrate e to the negative x squared on the interval 0 to 1? Okay. Well, let's see. So I got a definite integral now, so I don't have the plus c anymore. And let me go ahead and expand this out. So when n is 0, I have 1 times x divided by 1 times 0 factorial is 1. So x, that's the first term. Okay, when n is 1, I'll have minus x cubed divided by 3 times 1 factorial. That's the next term, okay? And then when n is 2, it's going to be plus x to the 5th divided by 5 times 2 factorial. Okay, and then when n is 3, I'll have minus x to the 7th divided by 7 times 3 factorial. Okay, and then plus next term will be x to the 9th divided by 9 times 4 factorial, minus etc. Okay, I'm evaluating this from 0 to 1. So now I can plug in the bounds. But by the way, when I plug in 0, like all infinitely many of these terms are going to be 0. Right? So all I have to do is plug in 1. And when I plug in 1, let's say I get 1 minus 1/3 plus 1 over 5 times 2 is 10, minus 1 divided by 7 times 6 is what that'd be. That's 42. Plus 1 divided by 9 times 24 is 216. Okay, minus, etc. So then if I just add up these first 5 terms there, the grand total from that is roughly about 0.7475. Okay, so the area under this curve from 0 to 1 is roughly 3/4. That's what we're saying. Okay. Now, we can also use Taylor's series for evaluating limits. Okay, so there's some limit calculations that are difficult, and like in this one. And by the way, some computer algebra systems compute limits in this way. So like, what if we had the limit as x approaches 0 of sine x minus x plus 1/6 x cubed divided by x to the 5th? Okay, I can't plug in 0, right? Because I can't divide by 0. Now, if I were to use L'Hopital's rule, which would be an option for this, I would need to use L'Hopital's rule 5 times to get the answer. Okay? So another option, rather than using L'Hopital's rule 5 times, to get the answer would be to use a power series. We have the limit as x approaches 0 of sine x is this guy right here. The summation as n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial. Okay, and then minus x plus 1/6 x cubed divided by x to the 5th. So let me go ahead and next thing, let's expand this out a couple of terms. We have the limit as x approaches, and by the way, make sure that your limit notation looks good. You're writing limit as x approaches 0, right? Okay, so if I expand this out, when n is 0, I have 1 times x divided by 1, that's x. When n is 1, we have minus x cubed divided by 3 factorial. Okay, and then when n is 2, it's going to be plus x to the 5th divided by 5 factorial. When n is 3, it's going to be minus x to the 7th divided by 7 factorial. Okay, plus etc. Okay, and then at the end of that, I've got the minus x plus 1/6 x cubed divided by x to the 5th. Okay, now here's x minus x, those are gone. Here's minus 1 over 6 x cubed plus 1 over 6 x cubed, those are gone. 3 factorial is 6. Right? So now I'm left with just 1 over 5 factorial x to the 5th plus, or minus 1 over 7 factorial x to the 7th plus 1 over 9 factorial x to the 9th minus etc. divided by x to the 5th. Okay, I still can't plug in 0. But I can, if we factor out an x to the 5th out of all infinitely many of these terms here, and then cancel it with the 1 down under, the leftover from that would be the limit as x approaches 0 of 1 over 5 factorial minus 1 over 7 factorial times x squared. Okay, then plus 1 over 9 factorial times x to the 4th. Again, I'm factoring out an x to the 5th from those terms and canceling it with the 1 down under, minus etc. Okay, well, all of these terms after the 1 over 5 factorial are going to involve an x term. And so now if we plug in 0 into all those terms, I got 1 over 5 factorial. 5 factorial is 120. 5 times 4 times 3 times 2 times 1. Right? I'm going to be adding 0 infinitely many times there for the rest of those terms. So the answer will be 1 over 120. Okay, now again, I can get the same answer using L'Hopital's rule 5 times. But this is just another option to do the problem. Okay. Now again, some computer algebra systems compute limits this way. Like if I do something in my calculator, do a limit calculation or something, or like on a computer, it's using these Taylor series formulas. Okay. So, all right, that's it with Calc 2. Okay, so here's the homework, the last homework there. Be sure to look at those problems when you get a chance, and we'll go ahead and stop the video right there.